All right, great. Everybody can hear perfectly well. So first of all, thank you all for coming out. I owe a big indebted gratitude to Marissa, Tom, Rico, our dearest bodyguard, Katie, Kat, who you met downstairs, Miko for the setting up the drinks and food, and then Jen and Gina, godsends for planning this. So round of applause. Thank you so much for putting this together. All right. Welcome to CTC. So for about folks who don't know who we are, proprietary trading firm providing liquidity to the markets. But I think what sets us apart from our competitors is our team first attitude. So we really do care about each other, and that's why I get to do the gratitude with Jen and Gina. It's all about caring about each other first, business second, and then technology all the way. So the caliber, I think, of the people I work with brings me to work every day. So that's a thank you to CTC for providing that. Case in point, Ron. So Ron is a skilled technologist. He's been coding since he was a wee young'un, Atari 400, back when dinosaurs roamed the earth. Is that what I hear? Yeah. Oh. Architect working at top tier kind of finance and tech firms, Apple, Morgan Stanley, our dear CTC. But I think what sets Ron apart is his mastery of the C++ language. So if we take history lesson with Ron, he actually did his undergraduate at Harvard in classics, Greek and Latin. Magna cum laude? Yep. Not too shabby there, sir, not too shabby. He then went to get his master's in computer science, so we're back in tech, don't you worry there. But I think it speaks volumes to C++ as a language, right? It's expressive, it's receptive. What does it mean to declare intent? And so I'm super excited for you to share your passion about the language with this fun community. So without further ado, Ron Ryan.
All right. Thank you, Erica, for that introduction, and thanks to everyone who set this up. I appreciate it. I used to do users groups in New York City. I used to go to the Lisp users group, and maybe like 5 people would show up. So this is like a huge crowd from my perspective. All right. So today I'm going to offer my reflections on reflection. Reflection is something that's missing in C++, and it's kind of like waiting for Godot. It never seems to arrive. It's always on the horizon. So over the years, I've had to roll my own solutions, and I'm going to share with you my techniques, and which, regardless of what's going to happen in the future with reflection, these techniques I think will be useful for solving other problems. So. Introspection and reflection. Introspection is an object can describe itself, and reflection is an object being able to modify itself based on that description. I included here, for the sake of the classics, know thyself, which is the inscription at Delphi. So there's actually 3 maxims at Delphi. There's know thyself, and the next one is nothing in excess, and the third one is certainty is madness, but how can you be certain of that statement? Also, the other one is a quote from Pythagoras. With a effective use of reflection, you can know the universe and God. I included that because I want to set the expectations of the audience. All right, so I must confess, I'm not quite sure what the state of the world is currently for real reflection. I hear it might be experimentally supported soon. Meta classes, which is a Herb Sutter offering, might do it. But the current approaches are that they're intrusive and they use macros. And I was looking for something that was felt a little more natural. All right, so I have some design goals for rolling my own. I'd like it to have real-world applicability. I'd like to be able to use it for things like serialization and testing and interaction. I'd like it to have a clean syntax and not be like too weird, easy to use so that people would adopt it. I'd like to create the illusion that it's part of the language. That's one of the things that C++ is good at, is sometimes if you have a clever solution to something, it looks like it was always there, as opposed to something that was discovered. I'd like it to be non-intrusive so that it can use it with existing types. This is one of Strustrip's points, is whenever you design something, it should be reasonable to implement it. And I'd like it to be flexible, but I can't really let the perfect be the enemy of the good. This isn't intended to solve all problems or address all the corner cases in C++, because there's kind of an infinite number of corner cases in C++. But I'd like it to be flexible, so I'd like to design it in such a way that you're not bound to a certain type of serialization or something like that. So my approach is going to use the oft neglected pointer to member. That's pointer to data member, but also pointer to member function. The pointer to member function is used a lot, but the pointer to data member is pretty neglected. And I include here a little snippet from Stack Overflow, where it says, I can't think of a convincing use for pointers to member data. Hopefully at the end of this talk, I might have some arguments against that. It's kind of an obscure syntax and an obscure idea. It's considered not very useful, but it's actually quite useful. So this is kind of like one of my design goals. I've got a quote here from Hesiod, like all of existence is a fight between chaos and order. And so what I'd like to do is, I noticed that a lot of serialization stuff in C++ is chaotic. It's imperative, and it's kind of like the kid who tells a story with a run-on sentence. He's like, and then I did this, and then I did this, and then I did this, and then you're like, there's no structure to the story. And you can't spot patterns with it. It's very difficult for your eye to spot like what exactly is going on here with this. So serialization and deserialization, I consider them to be high entropy if you use an imperative style, meaning that, like for instance, if you change a type and you were serializing it using an O stream and it's a string and you put quotes around it and then you change it to an int, the compiler can't help you and say, it's not going to be valid JSON now. So I like to think that the behavior of the program should be governed by the type, which is kind of one of the points behind object-oriented programming. So in order to roll my own, I have some ideas that will be useful, but while I talk about this stuff, I want people to look at the individual techniques that are employed because they can be useful in other circumstances. It's not just about reflection and serialization. There's some trickery going on, and some of the tricks, maybe you can use them individually to solve a problem in a clean way. So some of the techniques that I'll be showing you are, of course, the pointer to member, which is for data and functions that provides insight into a class. Using a singleton instance of an object whose function is to describe another object, this is what allows it to be non-intrusive. But if you want, you can make the reflection instance a reference to it, a member, or you can declare the reflection a friend of the class so that you can get access to private stuff. I'm also going to be using initializer lists. I kind of like initializer lists because they force you to boil down a problem to a problem that involves mapping, like you're mapping a string to something or an integer to something. And I kind of experiment with initializing the class with an initializer list to see if I can boil it down to data as opposed to imperative programming. One feature that's kind of nice about other languages is that you can declare a complex data structure as opposed to like populating it with imperative code. And so you can look at the declaration and see the structure immediately. I kind of like that, and I try to achieve that in C++ when I can. Another idea is that the initializer list of a singleton is inside the singleton and can reference its types. It'll become clear later why that's kind of a cool thing. Lambdas can be used to make specific things general. C++ is strongly typed, which is one of its virtues, but it can be frustrating because you might want to have a mapping, and the mapping requires uniform types, and lambdas can help with that. Templated constructors are also interesting. We'll be seeing some of that. The visitor pattern, I kind of like too. It allows you to sort of have a level of indirection for the visiting mechanism so that when you visit the members of a class and they expose their type, they're doing so to a visitor which decides what to do. And that allows you to have a generic algorithm for walking the class, but to have different behaviors when you do that. And I'm also going to show a technique for calling functions with arguments of arbitrary types using strings. All right, so here's, some of this is kind of pseudocode. It's like me formulating the problem and then working through it. So I'll be showing you the thought process towards heading towards the destination. So the first experiment is I have some struct, and it's got a couple of different types, and I'd like to have an initializer list that's a description of it. And I immediately bump into the problem that the left-hand side is easy. It's just a string. It's a label for the field. But the right-hand side is the problem, which is because C++ is strongly typed and you have different types, the initializer list will fail when you try to add it to a map or something like that. So the first problem we have to solve is how to make the right-hand side uniform and not heterogeneous. So, I can start thinking of solutions and, first start thinking of a variant, which is a way of creating a uniform type from heterogeneous types. But just looking at the variant, I'm already getting allergic to it. It's not heading in a good direction, and the variant will have to know about all the types that it's going to encounter, which makes it inflexible. You'd really like to have a mechanism that is sort of given a type, tries to figure out something intelligent to do with it. Maybe subclassing could do it, but this also feels wrong because it feels like a heavyweight solution. You have to have some factory producing these things, and you'll have to create a whole proliferation of types just to basically visit a data member. It might be as simple as an integer or a string or something like that, and you've got to have like a string member or something to handle it. Seems kind of heavyweight, so maybe we can do better than this. All right, so here's the solution that I'm going to use. The problem is the heterogeneous right-hand side, and one solution is using a lambda, and in particular, it's a templated lambda where a particular type is given as an argument to the function, and it returns a function that's uniform. This is kind of an important principle, that a function that returns a function of a particular type that returns a general type is a very useful thing. And as I said, I'm kind of like, the code is not in its final form, so I'm kind of working out the details, thinking through what this is going to look like. So I'm already getting a feeling that I'm going to have some sort of visitor, because one problem with using the lambda to make a particular type uniform is that the behavior is going to be encoded in the lambda. Now the lambda is doing a type of type erasure where you give it the pointer to member there, and it captures it and remembers it for you. And that's kind of a cool thing because the syntax of the pointer to member is awkward, and before lambdas, the syntax for doing all this work was really kind of bad. But if you capture it, it looks very clean actually. And then it cleanly solves the problem of the heterogeneous right-hand side. You can see that we're headed in the right direction, it seems. But there's a couple of problems with it that you can see, like there's a special function called make input lambda, which is someone has to remember the name of the function. It's not too difficult to remember the name of a function, but maybe we can do better than that. It's just one more thing they have to remember. And another problem is that we want different behaviors, and if we do it this way, we only get the single behavior of the lambda, and we have to duplicate it for the output side because we need a different function. It might be possible that you wouldn't have to duplicate it, but still, we should explore to see if we can do a little bit better than this. Okay, so the next thing we do is, again, we want the right-hand side is heterogeneous. We want to make it uniform. One cool mechanism in C++ for addressing this is to have a struct that is of a particular type, so it can be used as a right-hand side, but its constructor is templated. This is a relatively new feature in the language, and it is a very nice feature for doing this kind of thing, because what it allows is for the compiler to figure out a very complex pattern of behavior by matching an argument to the constructor, matching it against different possible constructors. So what we have here is the templated constructor is able to produce an input and an output side of the Lambda. And notice that the syntax for the initializer list is vastly simplified. So now it actually looks like it's part of the language. It looks very natural, and you don't have to remember the name of a function. So it should be accessible from any namespace. It's starting to feel like we're headed in a good direction. One thing that we're going to bump into is that we have to handle nested types. So let's do a little experiment to see where we're headed with that. So we create a struct nested and put it into what's going to be our little test class called the averager. And we're going to invent a role and see how it works out, which is I'm now starting to gravitate towards having a JSON visitor be the example visitor. So JSON has some known types like integer, string, and double. So we'll make a rule saying if it's a JSON datum, what you might consider like a scalar value or something, then that will be a known type. Otherwise, if it's unknown, then it'll fall through to a template that handles it. And the template will attempt to parameterize the reflection on the type of that class and chase it recursively. And as it turns out, this actually works. And the fact that it works is good news, because it means that we're kind of traveling along a path which is congruous with the nature of the problem. So we're kind of exposing the true nature of the problem. If you can find in a programming language a natural expression for the thing, and it's like this is like just a few lines of code, then it makes you feel good that maybe we can achieve our goal. Here's another problem we might bump into. I want to, for JSON serializer, maybe the fields are present, maybe they're not. Maybe you might want to write them out, maybe you don't. So let's go back to a previous slide. So part of what's happening there with the deserialization is somewhere in there, and this is kind of pseudocode, like if you actually look at the code, it's not really going to work. But it's trying to express optionality, and sometimes you demand that the member be present. Sometimes you're like, oh, it's okay if it's not. But you're doing it in an imperative way, which means that that you have to actually read all the code to understand what the policy is for that particular thing. This is a much cleaner solution and much more in the spirit of object orientation of C++, which is it's the type itself that governs the behavior. It's not because you're telling it to do something. It's the compiler is generating the code, the policy from the type. And now we're actually at a stage where we can start making interaction with the object live to test whether this optional concept works. So I create a new averager, and then this is kind of a Pythonic thing. You can just say the name of the object that you created. So I create a new A, which is of type averager, and then I just hit type A and hit enter, and it dumps out its internals with my JSON visitor. And then I say I want to set the optional int inside it, and then I ask it to dump again, and you'll notice that magically a new value has appeared in the JSON. This is good news. This means that we can have a uniform approach for any optional value. You have a type template that takes an optional, and it just, if the value is present, then, and this will work for different types. So it means that you don't have to write a lot of code. So all that code in the other slide that has to repeat the policy over and over again for each variable. Like that all goes away, and now you have a single policy. So you can just say, if I make it optional, then that is an indicator to the compiler that I want the optional policy. All right, so we've done pretty good with data members, and now we're going to get a little ambitious and see if we can have a similar sort of approach, complementary approach to having a class know about its functions, its methods. So we're going to experiment again a little bit and say, well, we're going to use a variadic template and say, given a pointer to a static method or a non-static member method, can we have the constructor create a lambda that will allow us to call it? So we're not really interested in visiting member functions. We want to be able to call them. And where we're headed with this is would be able to to call a function that takes strings and doubles and whatever, to call it with a bunch of strings. So this actually compiles, and what we're going to do is we're going to unify the data member and the method, the member function, under a class called member. And that way, so what will happen is the member templated constructor will dispatch either to this method class or to the data class to construct the lambda. And that means that you can have a single table of functions and data members. So this is a little preview of how to call a function with a bunch of strings. This is kind of a high-level view. But the basic process is you take the variadic parameter pack and you create a tuple out of it. And then you have a vector of string with the same cardinality as the tuple. And then you walk them in parallel and doing a lexical cast of the string to the type that's expected by the function at that position in the tuple. And then you invoke the method by telling the tuple to expand itself into an argument parameter pack, an expanded version of it. And so conceptually, it's pretty easy. You have to do a little bit of trickery and spend some time with the compiler to get it to work. But this actually does work. So now we'd like to start to get into the sort of introspection, allow the method to be able to describe itself. This is kind of a tricky problem. One of the nice things about Python is that it has this notion of a docstring. So you can have a uniform way of having a function describe itself, what parameters it takes. C++ doesn't really have that, but we can, move the ball forward a little bit by walking the arguments, the variadic arguments, and asking each one for its type. So at least we'll know what type is in what position in the arguments. And that's in the upper left, that's what the descriptor is. And then we'll put the return type in as the beginning of that. The typester is basically using the type info C++ library along with a demangler to get the symbol. That might not be portable, but it works pretty well on Linux, and it's useful enough that I think it's worth mentioning. Other things you can do is you can do some macro trickery. You have a macro that's inside the function, and the first time you call the function, it basically steals the arguments, the names of the arguments, and registers them in some singleton that's managing all this information. Another thing you could possibly do is make the docstring part of a constructor that takes two arguments, one of which is the docstring. That makes the initializer list a little more complicated, but it's a pretty straightforward way of documenting the function. Does anyone have any questions? Yes?
Yeah, actually, I have a couple, but like one is, and also a suggestion. I think like on Windows, you don't actually need the demangler. I know because I kind of tried that. But yeah, another one is, could you actually, in a couple of slides, could you have used std any, or would that be would that have not worked instead of STD variants? And
Okay. The question is, would standard any have worked instead of standard variant? And this is you mean back in the, one of the first slides? I suppose so. I just felt that I'm kind of a fan of this lambda capture thing, and I find it works for me. Off the top of my head, I can't picture the standard any solution. But it's certainly possible. I'm not saying this is the only avenue towards the solution. And this is kind of a runtime form of reflection too. I'm sure there's ways of doing it all at compile time with templates. So the answer is I don't know. The question was, I already repeated the question, right? Can you use standard any? And I guess my answer is perhaps. It's the Delphic maxim of certainty is madness. Okay, so, all right. I actually didn't talk about this slide yet, so I'll talk about this slide. This one's an important one. This is kind of the denouement of all the work we've done so far, which is, can we create an object that describes another object with a unified expression of its data members and its member functions? And the answer is yes, we can. And one of the interesting things is that the initializer list for a singleton instance that's done in the usual fashion of a static member, that initializer list is in the name scope of the class itself, so it can reference things in the class. This is really cool because in a previous slide, I was repeating the averager or whatever the type was over and over again, and I always hate that and try to find a way around that so that I can have a single way of expressing it so I don't make copy and paste errors. And you can do that. So that reflected type that you see is the averager that was passed into the reflection. It just says using reflected type, equals averager. And then the initializer list can see it. And one of the reasons this is also cool is that it means that if you're going to use macros, you only have to name the member. The macro can, obviously knows about reflected type. And so you get a really, really terse expression of what this class is. Discovering that the initializer list is in the scope of the class being initialized, I discovered that by accident, sort of, because I was doing the Lambda thing, and then make me a Lambda was outside the class. And then I decided to pull it into the class, and I recompiled, and it worked, and I was puzzled. I was like, I thought I was going to have to say reflection averager, JSON visitor, : make Lambda, and I didn't have to, and I was like, why is that working? And I thought about it, and it was because it comes after the : so instance equals everything after that is visible, has visibility into the class being initialized. And that's kind of a cool feature. Maybe you can use that in your own code somewhere. So that if you're saying, boy, I'm repeating this type over and over again in my initializer list, maybe you don't have to do it. Okay, so we'd like to kind of play with this and see what it does. So I have a class called averager, and I'll do a live demo of this in a little bit. I created a simple language, a simple syntax, which is the first argument is either a class or an instance of a class. And then the next argument is the function, and then it's whatever trailing args are needed by it. So if I say averager new a, I'm saying call the static function new on the averager and pass the symbol a to it. So it creates an instance of averager with the name a. And then I have some operators like question mark, which is dump what you know about yourself. And this is pretty cool. A can tell you that it has a field called total, which is an int, and it's got count, which is an int. It has an add function and an average function that returns double. And it's got some other toy functions. And if I just say A with no arguments at all, the default function call is dump yourself using the default visitor in your reflection definition. And then on the right-hand side, you can see that I'm going to start interacting with the class. I'm going to say add 10 and then add 20 and then take an average, you get 15. I say dump your internals. It looks good. And then I can delete it. The amount of code that's needed for this, the runtime support of that little interpreter that I showed you, it's very, very small because it's very simple. If it's a class, what it does is it looks up the class and sees if it knows it. If it doesn't, it looks up the identifier to see if it's an instance of a class. If it is, then it chases that, gets the class, and then calls the method with the argument. All right, I'm going to do a live demo. This is, I think Murphy's Law is also written on the Oracle of Delphi. It's very unprofessional to have to use the mouse. All right, so I'm running my program, and it actually ran a canned bit of code, so I can show you that. So at startup, I've got a vector of commands, which is just a bunch of strings, and that's what you just saw run. And there's one that's kind of interesting. It's where I say average or new y, and then I hand in a JSON string, which is the arguments to its constructor, you might say, to initialize it. And so what am I doing? I'm saying add 1, then add 10, dump your internals, delete, and then do the same thing with a y, dump your internals. So if we go back to the buffer, you can see that it ran that. So I said, add 1, add 10, got 11, said dump your internals, and you can see the total is 11 and a count of 2, which is what we expect. So I'm going to create another object here. We have a class called nested that it's aware of, so I'll try to do that. So it knows that nested has no methods, which is true. So I put in, oh, yeah.
Yeah, I was just wondering, you just showed, methods where you only have one instance of one type, but if you have like a polymorphic type, where you have, like, let's say you have add where maybe twins or, inverted mutated, would that, how would that actually appear with code had you not tested that?
It would not work. This is poor man's reflection. It does best with simple types. Like I said, C++ allows you such a multifarious number of possibilities. I'm saying, like, this is sort of like if you were reading in a configuration into a struct. You would say, oh, I have a kind of a complex struct, but it's complex because it's composed of very simple things. But this is not going to handle like template member functions and overloads and stuff like that. So we'll try to do an assignment. I wrote a built-in operator equals. So let's see what A has to say for itself. Yeah, that's pretty cool. A knows quite a bit about itself. So I've got that intrusive docstring example. I'll run that. That's what if you do the first call to the function, it registers the names of its variables. Oh. So. Oh, look, it picked up int I string s double d from the first call. So one thing you could do is is when you're registering the function is you could do a dummy call to it to initialize it if you wanted to pick up the names. It would be kind of nice if C++ had something like a superstatic variable inside a function which gets called with a normal initializer chain before main. Rather than be statically initialized upon the first call of the function. If you had that, then you'd be able to pick up a lot of stuff docstring style like Python has. So that would be a feature that I would actually like in C++ is to have some way of saying, yeah, this is a static variable in the scope of this function, but I want you to initialize it along with all the other global variables in the initializer chain at startup. Oh, I got my sig fault. But it wouldn't be a demo without that. So anyway, that's kind of the live demo. Usually when you seg fault, that means that's the end of the live demo. And let's see, I'll go back to my slides. All right, so an important part of this is the building blocks that went into this solution because they're applicable to other problems. For instance, the function that a templated function that returns another function has been useful in web programming that I've done with Tim, where you can create a handler for, so if you have to remember what you sent to some sort of web server so that when you get a response back, you can interpret it in light of what you sent. Then you can use that construct for that, the function that returns another function. So going through the building blocks again to recap so you don't forget them, we used a pointer to member, both data and function for insight into a class. We use singletons, and if you want to make it, technically a reflection should be the object knows about itself, so you could make the reflection a friend or a reference to it as a member so that the class, you could ask the class directly about itself. We used initializer lists to create simple declarative expressions of mapping to generate code with complex behavior from simple expressions. The initializer list of a singleton instance is inside the singleton, so you can simplify your type references there. Use lambdas to make the specific general. Use templated constructors to make conversions to uniform types implicit. We use a visitor so that the logic of what you do when you walk the data structure is not embedded in the actual walking. You're walking to get the type, and then you're exposing that type to something with a level of indirection so that, what you could do is you could create a superclass of your visitor that you parameterize on. Then you could have a JSON visitor and a YAML visitor if you wanted to, and it could be driven from a single instance of the reflection. And then the technique of calling arguments of arbitrary type using strings, which boosts lexical cast under the hood. All of these things can be used to create, like, let's say a system where you want to test some, I'm thinking like quants like to use Jupyter notebooks and Python because they like to experiment, test the corner cases of their algorithms and stuff like that. This is a way of doing that with C++, and you can actually use it for automated testing, saying, given these inputs, I expect this output, but you could put your expectations and everything into a text file rather than recompiling. Like Google test is awesome, but to change your test, you have to recompile. This way you say, oh, I found a new corner case, I can just put it into my text file. And you can also interact to see what the corner cases are. And so in conclusion, using these pointer to member construct, especially the pointer to data member, which is considered like not useful, we can construct something that's akin to a native reflection in introspection in today's and yesterday's C++. And we can achieve our design goals of having something with a clean syntax and real world usefulness. And along the way, we discovered some techniques that we can use to apply to other problems. And that's the conclusion of my presentation. Okay, so actually I came in right at the time. Right? Yeah.
I'll wrap it up. Any questions from anybody? I am not going to answer those. Oh, you're all yours.
Yeah. Yes.
This is kind of a personal question, but could you actually use your techniques to actually allow you to do contracts, like C++ contracts that were supposed to be in C++, I think 20 or so, but was pushed back? Repeat the question.
Oh, the question is, could you say it one more time, like the?
Could you use your this formant's reflection to generate test cases for contracts, like the ones that were
Okay.
proposed for C++ 20, but were kind of pushed because they weren't fully.
I don't know the answer to that question. Does anyone have any thoughts on that? That's can this type of infrastructure be used to test contracts? Yeah, I'd have to think about it. You know, I kind of like, this was sort of almost like a gravitational force for me. Like I was iterating and saying, okay, can I make it better? Can I make it better? Can I make it better? But I wasn't really allowing my mind to wander outside that iteration to say, I felt like I was on the right track, but as I said, like one thing you could do is you could say, oh, I want to do it at compile time because pointer to member should work at compile time too. It's just an offset. Yeah, unfortunately, I don't know the answer to that question. Yes?
So what are the language features besides superstatics that make this easier?
Reflection. That's the superstatics is like, would be nice because then you can actually pick up a description of the class that you're inside. Another thing is, I don't even know how this would work, but the fact that you have to parameterize on the type, the reflected type, and a visitor is a little bit of a problem, and you're only doing that for the data members. You don't really need the visitor for the member functions. And I thought a lot, like, is there a way that I could pass in the visitor not as a known type to the reflection, but as a template member function? I couldn't figure out a way to do it because the Lambda needs to be, like, the templated constructor, this is how I think of it. Templates are not real. They're kind of like I think the Velveteen Rabbit, which is, it's real if you believe in it. It becomes real. A template is just like an idea, like, hey, wouldn't this be a cool thing for a class? And then when you instantiate it, then it becomes real. But once you instantiate it, then it's no longer in, you know, the realm of theory. So you have a templated constructor. It's just an idea of a constructor, but when you invoke it, it creates a real Lambda, and that Lambda really needs to know the visitor type. Because what it's going to do is it's captured the type of the member variable, and it's going to call the visitor and expose that type to the visitor. So if the visitor is not known, I don't know how it could do that. And I can't, so I know that's one frustration I had, but I can't think of anything that the language would provide that would help me with that. So does that answer? Yes? No, this is just stuff that's in my head, actually, and in various repositories at CTC, I guess. Yeah, I mean, like, it's one of those things where, like, sometimes I write things and I like them, but I don't know that anyone else would like them, and I don't know that if I explained it to someone, they would understand why I'm enthusiastic about it. So this was actually a really good opportunity for me to present this because I hope you liked it, you know, being able to talk about this and explain it to people who understand it, that's cool. Yep. I don't know if, because when you say lambda equals and you do the capture and everything like that, you're creating something and assigning it to the variable. So yeah, I've thought about it. I mean, there might be a solution to it. You understand what the problem is, right? Yeah, it just feels like a shame, but I don't know. Like, I did spend a lot of time thinking about, like, is there a way around this? But I know that when you do a visit to like a variant or something like that, that you can provide a Lambda, one of which is auto, so that when it visits the variant, it gets called back with a, you know, if you wanted to say print, you don't have to, and the variant has 20 types, you don't have to have like 20 Lambdas. You can have a single Lambda that has auto and print whatever the thing is. But you're sort of like, the compiler has a lot more knowledge in that context when you call visit in the Lambdas right there. I don't know that you can assign it to a member variable and then come back later and say like, oh, use auto now. Does that make sense? Yeah, no, I think yeah, like when you say standard visit and then you have your variant type and the Lambda with auto, the compiler can see it all at once and say, oh, I know what auto means. Right, exactly. Yeah.
We might have a Zoom question.
Can
Sure.
I ask the Zoom question? I joined a little bit late, so maybe I'm missing something obvious, but can you make the whole reflection object context? I mean, like the addresses shift, right? They can be context, and the whole names can be context as well. So does it mean like the whole reflection of the thing might be context as well?
I don't know the answer to that. The initializer list is something that's done at runtime. So it's like basically a global variable. And before you hit main, it's running code to populate these things. I'd have to experiment with it. It's a good idea, but my suspicion is that you can't do that. Because they're like, when the Lambda is doing capture, it might need to grab some memory, you know, to store whatever it's capturing. So I think it's probably too dynamic for a const expert, but I don't know.
Right. I just double check. Initializer list is const exp starting 14, C++ 14. So
it might be worth
just to let you know.
Okay, it might be worth experimenting. I'd have to think about it.
Right.
Any others?
Thank you.
Tim, did you have a question? Oh. Yeah.
For the superstatic concept that you wanted for the intrusive.
The intrusive.
You considered the constant.
No, I have not. That's a.
New in C++ 20, it sounds exactly like what you described. It's initializing compile time, but it's a variable. It's not const. You can modify it at one time.
That's a very good idea. I was unaware of that, and I'm going to look into it right away. So maybe the thing that I want is already there. I just didn't know. Thank you. All right, and thanks to you all for coming, and thanks to everyone who set this up.
No, you're welcome. So again,
Recording
C++,
stopped.
it's dynamic, it's growing. You know, we've got 23 coming out here, maybe. Yeah. So we need to do more of these. So I know Matt did the first one, Mike did the second, Ron's done the third. We're excited. I want to thank Rob for resurrecting the C++. I know we've got Sucrat potentially, a Res potentially, so this is a challenge to throw out there. Who's got some great C++? The community's here. Let's resurrect it. Let's have fun over COVID. So thanks very much for coming.